Hello, welcome to the cold day video. It's the day four notes from chapter 10a with series. We're going to continue with the power series that we started on yesterday. All right, so we already did this example in class. Just quick recap. We write out a few terms. We notice that it's geometric. Our value of x plus 1. We call it a power series because terms have increasing powers on x, or in this case, x plus 1. We use our infinite geoseries sum formula to eventually find a function that this series converges to. So here we have a function that's equal to an infinite series. And of course, it only works when your R value is between -1 and 1. So we swap in our R value to find what we call an interval of convergence. This relationship up here holds only when x is between -2 and 0. So we could actually say the series is equal to this function. Okay, next page. Here we saw a second quick example. In this case, again, geometric, r equals x, using our sum formula to find the function to which the series converges. Interval of convergence, meaning this relationship holds when x is between -1 and 1. Okay? I really want to stress that these relationships are important and useful, but they only hold true when you live within your interval of convergence. Okay, on to the new stuff. Got a couple more examples on this page, starting with the series at the top left. I've got terms of the form cosine x raised to the n power. Okay, well, we can write out a few terms if we need to see a pattern. It is still geometric. We're multiplying each time by cosine to get from one term to the next. So we could say r equals cosine. And again, we're using a1 over 1 minus r to find the function to which this series converges. Okay. Interval of convergence, where does it work? Well, we need cosine of x to be between -1 and 1. And if you remember your trig, you know that cosine is always between -1 and 1. Well, except for the occasions where cosine is exactly equal to -1 and 1. So there are a few values, well, really it's an infinite number, but there are some values where this thing does not work, and we have to think about where would cosine be equal to 1 or -1? Well, it's exactly on the integer multiples of pi. Cosine of 0 pi, cosine of 1 pi, 2 pi, 3 pi. These are the locations where cosine is -1 or 1, and therefore our relationship breaks apart. And if you like, there's a graphical representation on the right that has the actual function of 1 over 1 minus cosine x in blue this time, where the red is a representation of the series. Okay, moving along. Second example on the page. As always, if you feel the need, you can write out a few terms to make sure you're aware of what patterns are developing. Okay, I see a first term of 5 thanks to starting at n equals 0. Then after that, we're multiplying by copies of x plus 4 over 3. So again, geometric. This time, r equals x plus 4 over 3. I'm going to put that whole expression between -1 and 1 to establish convergence. And now we're going to solve the inequality, perhaps multiplying everything by 3, and then after that, subtracting 4 everywhere. And we see that our relationship above is going to hold true when x is between -7 and -1, not inclusive. The bounds don't work here. Okay, the bounds, we don't want x plus 4 or 3 to be equal to 1. Okay, so once again, applying our formula, a1 over 1 minus r. I do clean it up a bit here. I think the easiest way through this is to multiply everything top and bottom by 3 first. to clear out the fraction and the fraction, and then you can start distributing, combining like terms. So yet again, we have this result where a certain infinite series is equal to what looks like an algebra or calculus function. Okay, we're going to come back to this example in just a bit. But on to the next page. Quickly revisiting our definition, we said that these series today are power series because they involve raising some variable to a power, an increasing power from one term to the next. I'm going to expand on that a little bit. The formula that you're seeing at the top here, where x is by itself being raised to various powers, we say this power series is centered at x equals 0. Now, what does the word centered really mean here? It's actually a reference to the very center of your interval of convergence, if you were to calculate that out for a specific example. Okay, so when we talk about centering a series, we're talking about the very center of the interval of values where a relationship holds true. Now, the second equation on the page is really the same as the first, slight modification. Now we see x minus a raised to various powers. And of course, it could be a plus as well. This is just communicating that we can still treat these things as power series if you have, x plus 1, x minus 4, things like that. And what's happening in those cases is you're adjusting the center. Whatever this a value is, that's going to be the center of your interval of convergence. Here it says center of the series, which isn't necessarily wrong to say, but it's really more specific to say it's the center of the interval of convergence for the series. And throughout the rest of this chapter, and really more so in the next chapter, you're going to learn a lot about the convergence of these things. And there's three different scenarios. Um, what we've seen so far really corresponds to the middle scenario. We've found some intervals of convergence around a certain center. But there are some series out there that actually converge for all values of x. Or they might converge at just the center. There's just a single x value where you achieve convergence. Okay? I don't need you to worry about these cases too much right now, but I'm just putting it on your radar as we'll come across it eventually. Okay, on to the next page. Now, why do we care about a function being written as a series or vice versa? Well, there's a calculus answer to that. Here's where we're at. We've seen some functions can be represented by a series as long as you're in your interval of convergence. If those functions are differentiable or integrable, then the corresponding series would be as well. And this is helpful for us because, as you'll see eventually, sometimes it's easier to do the calculus we need to do on the series version as opposed to the function. Okay? Now, how do we find the derivative or integral of a series? Well, when it comes down to it, a series is just a bunch of terms, and yeah, there's an infinite number of them, but the rules for differentiation or integration remain the same. You could just apply your shortcut rules to every individual term of the series, or even the general term. And general term is just another name for the formula that we see in the sigma notation. You can apply a derivative formula directly onto that formula. Okay. Now, when we find the derivative or integral of a series, we do have to be a bit careful. Uh, a lot of times, the original series that we started with had an interval of convergence. Okay, well, does that change? Can it change when we take a derivative? Here's what I say. I say the derivative or integral version will have a similar interval of convergence. If there is a change, it's probably going to be at an endpoint. Okay, and this is another thing that I'm putting on your radar that you really don't have to worry about until next chapter. Okay, let's look at an example. I'm pulling in the same example we already started on a previous page. We already established that this series is geometric. Here I'm going to give it a name, like we would name a function f of x, and we already established that it's equal to 15 over negative 1 minus x as long as you live between negative 7 and negative 1 for x. Okay. Well, we're going to find the derivative of all of this. We're going to find an f prime, and I'm going to take the derivative of both variations of f. I'll take the derivative of the series and also the function because I think we know how to do both. And we'll end up with a new series and a new function that are going to be equal to each other. So let's start with the series. I know this formula looks a bit complicated, okay? Um, but if we're going to differentiate with respect to x, you can temporarily treat n as a constant. I know n changes from term to term, but when we take the derivative of each term, n doesn't change, okay? And big picture, this is polynomial in nature, so I can use a very basic shortcut. I can take my previous exponent, multiply it by whatever multiplier was already there in the front. So 5 times n becomes a 5n. And then, okay, whatever was being raised to the n power, well, we're going to reduce the power by 1. So now I'm going to see x plus 4 over 3 to the n minus 1. Now, if you're wondering about this extra division of 3 that I'm showing, well, that's from chain rule. Remember, we would have to then take the derivative of this interior part. What's the derivative of x plus 4 over 3? You could think of it as x over 3 plus 4 thirds. Derivative is going to be 1/3, hence we've got a 1/3 multiplied in here. And what I want you to note about this result is that it's not geometric. The original series was geometric. This one is not. And it's because, even though I do see some base raised to a power with n, I now also have an extra n multiplier. This n right here is not the same in every term. So we've introduced a multiplier that's not constant, it's not common. If you were to write out terms of this, which I invite you to do if you like, you will see that you no longer have a geometric progression. Okay. Now, what is this series equal to? Well, if I knew that the original series was 15 over negative 1 minus x, I can set this new series equal to the derivative of 15 over negative 1 minus x. It's a pretty easy one to do. Try it on your own if you like, but here's the result, 15 over x plus 1 squared. Now, as far as interval of convergence, for now, I need you to just take my word for it. It's going to be the same as what it was originally. We haven't let you, or sorry, we haven't yet learned how to determine if there's a change, and you don't have to worry about that until next chapter. Okay, so just take my word for it. Okay. Now, what's especially useful about all of this work here, I've got my note over on the side. Previously, we were limited. If I wanted to find a function that represents a series or vice versa, I needed the series to be geometric because the only tool we have for figuring out the function was a1 over 1 minus r. So now, all of a sudden, for the first time, we have a function for a non-geometric series. We couldn't have pieced it together using the old technique. We were only able to get there using calculus, using derivatives. Okay. And I think that's good for this slide. We'll go on to the next. I think we have one more example. And this time, we're going to take an integral of a series. So here I have an f of x equal to an infinite series. We have not seen this one before. Okay, I'm going to do a lot of the same analysis we've been doing. It is going to be geometric. Write out some terms if you need convincing. The r value, no surprise. I see negative 1 to a power of n. I see what's really x squared to a power of n. Put that all together, we get negative x squared. Now, typically we solve these for x, so I can start the same way as usual. I can put my negative x squared between negative 1 and 1. Maybe I multiply everything by negative 1 to remove the negative from x squared. But remember, when you multiply by negatives in an inequality, you need to switch the direction of your inequality symbols. And I personally don't like this ordering. I like it to go from least to greatest. So for my next line of work, I'm not really doing anything new. I'm just changing the order. Okay. And as you look at this, you might notice that x squared technically can never be less than 0. Once we square something, it's not going to be negative. So even though I have negative 1 to 1, really and truly it's 0 to 1. Okay. But ultimately, none of that matters too much because to get from x squared to x, we have to be a little bit tricky with it. I'm not necessarily doing an algebra step to undo the squaring here. Think about it. If I take a square root of x squared and then I take a square root everywhere else, all of a sudden I have a square root of negative 1. We do not want to be dealing with imaginary numbers in this class. So instead of trying to get there algebraically, I'm just using common sense, intuition, okay? What type of numbers would I be able to square and end up with the result between 0 and 1? Well, it ends up still being all the numbers between negative 1 and 1. Those are the numbers that you could square and have a result less than 1. Okay. We should kind of just know that already. But if that's, new to you, now you see it. Okay. So our interval convergence for this thing is going to be from negative 1 to 1. Back up to the yellow. Applying a1 over 1 minus r, we get to a function that is equivalent to our series. Careful with the minus minus. So this series is equal to 1 over 1 plus x squared. When we live within our interval, you could see some graphical evidence to the side. But I want to take the integral of this thing, okay? Down in the orange here, this is my integral of the original series formula. Again, for the calculus steps, we treat n as the constant, x as the variable. So negative 1 to the n, that just carries right down as a multiplier. X to the 2n, let's raise the power by 1, as we've done in the past, and then, of course, we divide by the new power. So here is your new series that is the integral of the previous, and therefore I could set it equal to the integral of the previous function. And wouldn't you know, this is a top 20, and therefore it's equal to the arctangent of x. And yeah, I didn't put bounds, so we should be thinking about plus c's. I'm not really worried about that right now. The bigger idea is we now have the series version of a pretty common calculus function, arctangent of x. Okay. Interval of convergence. It turns out there is a slight change compared to the original series and function. The lower bound is now inclusive. I don't need you to know yet why that is. Okay, we'll talk about that later, but just be aware that there is a change. Okay. And this particular series and function that we've landed on, the series for arctangent, is going to be really important in the coming days and weeks. In fact, there's a collection of 7 very common series and function relationships that you are going to have to memorize. This one is going to be on that list, and I'll tell you more about it next week. The list might actually already be up on Schoology in the notes folder somewhere if you are curious to look ahead. Okay. Last slide, nothing really to do here. I'm just showing you the formal definitions of what we did today, pulled from a textbook. I know it looks like a lot of gibberish with all the symbols, but if you're someone who likes more of the formality, feel free to peruse this and let me know if you have any questions. Okay, thanks for watching. I'm sure there's a Delta Math, although I have not changed the homework schedule um, based off of losing a day, so I don't remember off the top of my head what's due when. All right, email me if you have any questions. Have a nice weekend. Goodbye.